That would make my job so much easier if no one showed up. They post their Dean Awards on, what is this, University of Derby? What is that? Oh, it's in England. Huh. I'll give it some more time. I don't know who's watching right now, but I guess hold on tight. If no one shows up, then I don't have to do anything. So here's to hoping I get to be lazy. I feel like I'm one of the viewers. Who's the other one? Oh, I got 3. Okay, okay. Oh, hey, Breen. Thanks for coming. Honestly, this one's gonna be real half-assed. It was made kind of last second, and I've got a lot going on right now. I think, unless it's me, you're the only one watching. You could, yeah. You might as well at this point. Okay, so I'm not one of the viewers. So it's Brain and probably Jonathan, maybe? Is that Jonathan there? Oh, we're up to 3. I might actually have to do something. Actually, I could start by making the chat actually work. Hey, it works. Hello, everyone. Oh, we're up to 4 now. Looks like I'm gonna have to present. Fuck it. I made the slides, I might as well present. Okay. I doubt people would be trickling in right now, and if this was held in person, we'd have just about the same amount of people. I'm sure Braden could attest to that. Welcome to the 10th week. I think last week they went over the CCPC solutions. Hope you guys found that interesting, but now it's my turn to talk. And quite honestly, I don't know what I'm talking about most of the time. So, first slide. We're going to be talking about suffix trees today. And that's kind of, well, I guess it's illustrated right here. So we have a string, and we want to find if we have a string C here, and we have a string H. Now, the question normally is asked in the form of, is H a substring of C? And with a small word like this, we can easily say, yeah, that H is a substring of C. But obviously, as the amount of letters in the string goes up, or the amount of strings go up, we're going to run into some problems. And there's a couple of ways you can deal with this. One of which is the suffix trie. Now, a trie is not very similar, or it's very similar to a tree, and it's a little bit more abstract, but it's like a tree if each individual character was mapped out, and if actually I don't know exactly what the conditions are for a trie, but I am told that this data structure is called a trie, so we'll just go with it. So imagine each individual character as what is it called? An edge on the tree. So if we wanted to make a trie of the word, I'm going to use the liberal use of the word, but if we wanted to make a trie of the word big, we would have to pretty much get every sequence of characters that could possibly be coming off of, I. So you would have, I think, I, G, G, and E as separate edges on this trie. And then coming off of it, you'd have all the different possibilities of what could come off of it if it was some kind of substring. So as you would go down this tree, you would pretty much be checking whether or not it's it's a substring. So we'll go through each letter, check if it's part of the sequence, and then if it's not, then it'll just kick it out, and it'll say no, it's not a sequence. Implementation wise, it's kind of like this. So it creates an edge for every suffix within string t and adds a terminating character. So this terminating character at the end is kind of it's a way of telling it that it's while it's traversing, that it's reached the end. So if at the beginning it doesn't even start with a B or an I or a G or an E, then it would just go to the $sign terminator symbol, and that would immediately just return none. It has this pretty much at the end of every single node. So each branch connects to a node. Each node has two branches, one of which is going to be the terminator symbol. And then it'll traverse this node until it either falls off, which is to say that it's not a part of the substring, and then it returns none, and it says that this is not a substring of this word. Or it returns the node at the end of the path. So that could be, if it returns the node at the end of the path, then it knows it's a substring, and then it will return true. Runtime complexity. So as any kind of brute force method, you are running into a very bad runtime. We're looking at like n to the power of 2. I think you can see why it would be like that. Just going off of the code, if the chat window wasn't blocking that, of course. I should probably fix that. Give me 2 seconds here. Make that over here. Yeah. So you can probably see by the code itself that it's not the most efficient thing on the planet. And its lack of efficiency shows in its runtime, which is very, very slow. So we want to move on to something a little bit more practical. So one thing about the try that's kind of stupid is that you could go through each individual letter, but you're wasting time doing that. And if you know that the sequence after that is a certain sequence, then you know that you can kind of coalesce the non-branching paths, not branding, branching paths, and kind of relabel the edges. So that is to say, we take the individual letters and then we kind of move them up into their own node. That way it saves time, and that way it knows when to stop if it has to. You could also put weights and kind of like labels at the end of each, the end node of each branch, that kind of tells how large it is, what like it would normally be 2 ints, but it would put, oh, sorry. It would put, I forgot what I was saying. So it would put the number of nodes there are leading up to the edge, or sorry, leading up to the final node, and it would also put, its level and stuff, so that you can kind of memorize it. But beyond that, you could also build a single edge tree, which is to say just one big line down representing only the longest suffix, and then, add some more trees that include all the other ones. But that's basically just a try at that point. And though these two methods sound like they could be viable, they do almost nothing to get us to a more favorable big O. So option 1 and 2 both have a time complexity of n to the power of 2 still, despite putting in that work. So we haven't really gone anywhere. And then option 2, in terms of space, it makes it n instead of just the number of words, basically, rather than, you know, every single character, because we're coalescing all these individual characters into something a little bit more compact. So the naive suffix tree is on the right, and the suffix trie is on the left. Now, as you can see, it's a lot more work to implement the suffix tree for very, very little benefit, if any. Unless you're brute forcing it and you're running into space complexity problems, then that's honestly, you're better off sticking with the trie. So there's a solution, even though it seems like the only two options have been exhausted. So tries and naive trees don't work, and therefore maybe it's impossible to run at a respectable big O value. Well, in this one particular case, and I don't mean to treat anyone here like an idiot, because you probably know this better than I do, and you know this, what I'm about to say next. So if big were to be very big, like I'm talking like n to the 1 million big, then our code's gonna slow down, if you could guess that. And that would slow down even more and more as that number gets bigger. So a trie is not going to work, and a tree is sure as hell not going to work. So there is one algorithm that someone developed that's actually known to travel in O to the n time. It is known as Yukonen's algorithm. So I have a visualizer here, which is about the best I can do, because this algorithm seems a lot more complex than I have time to learn. Does it stream the screen? Or does it stream... Oh, it does. Cool. Alright. So, this is kind of a visualization of what goes on when you're constructing the tree. So we can just do anything like, I am a big, yes. Very normal sentence. So it'll go through, creates the I first, goes through all the different branches, and then it starts to kind of do this weird thing that I really don't understand. It almost splits it into something easier, and then it restructures the tree, from what I can tell. And if it sees something that's similar, it kind of consolidates again and again and again until it is done doing its thing. Okay, point is that I don't know what I'm talking about when it comes to Yukonen's algorithm. It's way beyond what I know. And if you want a good explanation, I'm not going to pretend to try to deliver it to you. It will come out as bad as the rest of the presentation so far. So, if you want to know more about Yukonen's algorithm, you can Google it, watch videos, and I'm pretty sure there's a very nice explanation posted somewhere on Stack Overflow, probably in a very deep, dark corner. So if you want to know more about this, you should look it up, but I'm not the guy to tell you how it works. Let's see. I would ask if there are any questions, but I'm pretty sure I can't answer any of them, but I'll give it a shot anyways. Do you guys have any questions? Alright, so the contest today has the first 3 questions as what I think are suffix tree type questions, and the rest are random ones I picked off Caddis. So at 6:30 those will open up, and if that's it, then I am done with this presentation. I'll wait a couple of minutes for questions, but I doubt I'll get any, and then I'm gonna go peace out for the rest of the night. All right, it's been fun. I hope you guys, your finals go well, and yeah, have a happy long weekend if you're in the workforce or the university force. I will see you later.